When you push a magnet into a coil, you get a brief spark, but the moment it stops moving, the current fades to nothing. That temporary burst of energy was the primary limitation of 19th century physics. A single spark is a laboratory curiosity, but it cannot power a factory or light a city. The challenge was maintaining that flow of energy. Faraday and Henry proved that changing magnetic fields induce electric current. They understood the physics, but maintaining a constant flux change was a mechanical hurdle. Nikola Tesla developed a design that replaced the linear motion of early experiments with a rotating armature, allowing for uninterrupted power generation. The alternating current, or AC generator, solved the problem of temporary power. It serves as the physical bridge between raw mechanical motion and the electrical grid. The engineering logic of the generator is centered on one action. Instead of moving a magnet past a wire, you constantly rotate a wire armature inside a stationary magnetic field. As long as that coil keeps spinning, the magnetic flux passing through it is constantly changing. The induced current never reaches zero. The generator translates circular mechanical energy into a rolling electrical wave. The hardware features magnets providing a steady magnetic field around a spinning central shaft. Mounted on it is the armature, a wire coil sweeping through the field lines. The coil connects to slip rings, where stationary carbon brushes slide to draw current outward. This arrangement exploits the laws of induction in a cyclical, repeating manner. We measure magnetic flux, the coil's area exposed to field lines. As it rotates, the captured field changes. We track its angle, defined by angular speed omega over time t. Thus, flux equals field strength B times area A multiplied by the cosine of omega t. Because the rotation is circular, the flux trapped by the coil follows a perfect mathematical oscillation. Faraday's law establishes that the induced voltage is the negative rate of change of that flux through the turns of the coil. A time derivative of our flux equation pulls angular speed omega to the front and transforms cosine into a sine function. Combining the constant variables, turns, field, area, and speed, into a maximum voltage, E0, gives the final output, E0 times the sine of omega t. The rules of calculus clearly prove that a constant circular mechanical input must inevitably result in a perfectly sinusoidal electrical output. This resulting electrical waveform is a sine wave that continuously flips polarity. Voltage is zero when flux is maximum, but reaches its absolute peak at 90 and 270 degrees, when the coil is parallel to the field and the rate of change is highest. Because the voltage periodically reverses its sign, it forces electrons to change direction. This is alternating current. The mechanical frequency of the armature determines the exact rhythm of the energy supply. In India, these armatures must rotate exactly 50 times every second to maintain the 50 Hz grid frequency used across the country. That rotation is often provided by the force of water falling from hydroelectric dams to turn the generator's turbines. Thermal power plants use coal or nuclear fuel to create high-pressure steam, which provides the mechanical force required for rotation. A single industrial-scale generator can produce 500 megawatts of power, enough to light 5 million 100-watt bulbs at once. From the water in a dam to the steam in a nuclear reactor, the mechanical source varies, but the physics do not. The electrical supply for an entire city is the result of a wire loop turning through a magnetic field.